Now let's see what's going on with 4.5 where we learn about holes. So this is a good one. Hole or vertical asymptote, all right? Here's the deal. If something is in the denominator, it can be a hole, it can be a vertical asymptote. The big question is, does it cancel out? Is it also in the numerator? Then it's a hole. Is it only in the denominator and not in the numerator? Then it's a vertical asymptote. Only in denominator. All right? So let's go look right here. Here I have an x minus 2 in the denominator. Not in numerator. That makes this a vertical asymptote at x equals 2. That one. Okay, then we look over here. I have this in the denominator, but I also have it in the numerator. That means that they cancel. Boop, boop. Which makes this a hole at x equals 2. See? Easy peasy, right? That's literally it, you guys. That is it. Okay, let's keep it going. That x plus 2, it's in the denominator. Is it also in the numerator? No. So does it cancel? No. So what is it? Vertical asymptote. At what? At -2, because we need it to turn into 0. C. And finally, right there in the denominator, I got the x plus 2. Right there in the numerator, I got the x plus 2. They cancel out, meaning this is a hole at -2. Oh shoot, did I put this one as the hole? My bad, vertical asymptote at -2. I should have written this here. And that one there. Okay. Latifa says that the graph of blah 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 is the same as the graph of blah blah blah. Is it correct? Well, let's see. This graph has an x plus 5 and an x plus 5 that cancel out. So f of x is really just x minus 3. But it's not just x minus 3. It is x minus 3 with a hole at what we canceled, which was -5. That's what f of x is. G of x has a 5 and a 5 that cancel. That's just a constant, you guys. I can't make 5 be 0 like I could make x plus 5 be 0. So g of x is just x minus 3. No hole. All right. I bet some of you are going now, wait. Why is there no hole? We canceled something out. We did not cancel out something with an x. We did not cancel out something that had an x, all right? So that means we did not cancel out something that could have been 0. Okay? That's the big key. If you cancel something out that could have been 0, well then what would have made that 0 is a hole. We cannot ignore it. We got to put a hole. But in this case, that wasn't the case. So, all right. We're going to create a rational function that has this description. This one has a hole at x equals 5. That means it is a x minus 5 on the bottom and 1 at the top. And frankly, that will do. But you could add something else there just to make it interesting if you want it. Okay, I want a hole at 5, but also a vertical asymptote at -2. So, let's go. A hole at x equals 5 means I need an x minus 5 and an x minus 5 to cancel. A vertical asymptote at x equals negative 2 means I need an x plus 2 in the denominator and no x plus 2 in the numerator. And that's it. Okay. Ooh, look at this one. Holy moly, this one has holes everywhere. All right. This one has an x minus 3 that cancels, an x plus 1 that cancels, and an x minus 6 that cancels. And frankly, this is enough, all right? But if you want to make it more interesting, you could give it something else over here. Something. You could throw stuff in, all right? As long as these guys are there, we're good. Let's select all equations that match this graph. Well, let's go learn about this graph. This graph has a vertical asymptote at 3, which means it has an x minus 3 in denominator. This function has a horizontal asymptote at 0, at y equals 0, which means that the degree is bigger on bottom. That's according to Bobo Button. Look back at old videos if you don't know Bobo Button. This graph also has a hole at negative 1. That means that it has an x minus 1 on the top and 1 on the bottom that cancel. So let's go see. Which of those functions do all of that? Ooh, we want an x minus 3 and an x minus 3. These cancel, so this cannot be it. This is bad. 1 over x minus 3, where x cannot be negative 1. Oh my god, I just realized I'm so wrong. A hole at x equals negative 1 means I need x plus 1 right here. Sorry, you guys. Correction. Big correction. Okay. Okay, which makes this okay. If I have 1 over x minus 3, I'm bigger on bottom, I have the x minus 3 in the denominator, and this is going to take care of the whole. X equals negative 1 is a whole. So this one's good. This one is bigger on bottom. It has an x minus 3, and it has the x plus 1, x plus 1. This one is also good. This one has the asymptote and the bigger on bottom. It does not have a hole. It's missing the hole, so that's no good. And then this one, I'm willing to bet we got a factor to find out. All right, here we go, you guys. If you are not comfortable with factoring, all right, a lot of the time, the thing you need to factor will be this kind of thing. So please just remember this at least. Can you find two numbers that multiply to make that number and add to make that number, okay? This is the most common type of factoring you're expected to do. So if you can at least just find two numbers that multiply to make negative 3 and add to make negative 2, you can get like maybe 60-80% of the factoring okay. So what multiplies to make 3? 3 and 1. How can it make a negative 2 when I add them? If the 3 is negative. And now does it multiply? Yes, it does. And so that means this factors to x minus 3 and x plus 1. These two numbers that I found are the factors, all right? Which means that E is actually exactly the same as C. So it's fine. Okay. And lastly, write the equation of a rational function with a hole at 3, a vertical asymptote at negative 2, and a horizontal asymptote at 1. Okay, let's go see it. Hole at 3. So x minus 3 on top, x minus 3 on the bottom. A vertical asymptote at negative 2. So x plus 2 on the bottom. And I want a horizontal asymptote at 1. So that means that horizontal asymptote of 1 means my exponents are the same. So right now, currently, the degree of the top is smaller than the bottom. I need to add an x something to the top. Now my exponents are the same. It's squared and squared. And now with their coefficients, if I divide, it's going to give me 1 because everybody's coefficient's the same. And that's good enough. You can add something here as long as it's not like -3 or +2. You could put something else here, or you could leave it just x, and that would be fine. Okay. All right. And then now moving on. What is the equation of the oblique asymptote of this? Well, we're just going to do 2 steps of a division problem. So we put 2x squared and we put x minus 2. So this is 2x. And then this is negative 4x. So then this is 8x. So then this is 8. So it's 2x plus 8. This one. All right, I did it fast because I've done this kind of problem before. So go back. If you're uncomfortable with division, go back to division problems. If you're, anything, just go back. Okay, and now solving equations, you guys. I'm gonna do this because I feel like we need to be good at this. Look, our go-to solving an equation is to just isolate x. That's all we want. We just want to isolate x, okay? Now over here, I can isolate x. I have 2 choices. The 4 is for sure in my way. So I can either get rid of this 4 by distributing it to get 8x minus 40. Oh, why 40? It's 20. Equals 12, all right? Or I can divide it by both sides, cancel it out, and get 2x minus 5 equals 3. Both of these equations, if you go solve them, will give you the same exact answer, okay? So your choice, do what you want. It won't always divide nicely. 12 divided by 4, we were lucky that it was nice. It's not always gonna be nice. So definitely knowing how to distribute is the foolproof way you could use every time. But anywho, and now I'm gonna solve just this, but you can solve either of these using the exact same tactics. What you do is you first get rid of what's furthest away from the x, which is the -5. You do the opposite to both sides of the equal sign. So you do +5 on both sides. And you get 2x equals 8. And now divide by 2, divide by 2. The number in front of x, when you want to get rid of it, you can only do that by dividing. And so you get x equals 4. Okay? Same thing you would have gotten here. And then this equation, as ugly as it may be, is exactly the same as this. All right? You start by getting rid of what's furthest away from the x, which is the -7. So we're going to add 7 to both sides of the equal sign. And we get 3/4 x equals -1 plus 7, which is 6. And now I have to get rid of this 3/4. You can do it the way I said before, by dividing by 3/4 on both sides. That totally works, all right? And if you have a calculator, you're pretty much golden as long as you're careful to put this in parentheses in the denominator. If you do it by hand, you can keep, change, flip. Okay? And so then this becomes 3 goes into 6 twice. 2 times 4 is 8. X equals 8. What I would have done, just to show you what I would have done, at this stage in the game, instead of dividing the 3/4, I would have multiplied by the reciprocal. The reason being that you can cross-cancel stuff out. So if I put the reciprocal right here, everything will cross-cancel out, and I'll have x equals. And then here we'll cross-cancel, and then 2 times 4 is 8. So it's the exact same thing that happened last time, just a different way to think of it and look at it. Alrighty, you guys.